Welcome to another video on thermodynamics. In the last video, we have discussed second law of thermodynamics, heat engine, and the efficiency of heat engine. In this lecture, we are going to derive the expression for pressure exerted by gas molecules on the walls of container in terms of density and in terms of kinetic energy of gas molecules. Let's get started. These are the sample questions from past papers. Let's just see. Derive an expression for the pressure of a gas molecule inside a container in terms of its mean square velocity. And then, given figure shows a cube of length L, pressure exerted by gas molecules in one dimension inside this cube equals Px m over v in Vx square, where this Px is the pressure in one dimension, m is the mass of one single gas molecule, capital N is the total number of molecules, whereas this Vx square is the average square speed of the molecules in one dimension. Deduce an expression for the total pressure exerted by the gas molecules inside the cube. Let's just first see the outline. What is pressure? Pressure is the force exerted by the gas molecules on the walls of container per unit area, right? So in order to calculate pressure, we must calculate force and area. How do we calculate force? We know that force is rate of change of momentum. How do we calculate this change of momentum? We know that change of momentum is final momentum minus initial momentum. And what momentum exactly is? It is the product of mass and velocity. So first we are going to calculate initial momentum and final momentum. Taking their difference, we'll calculate change in momentum. Dividing it with the time that the molecules took to change their momentum, we'll get rate of change of momentum, which is nothing but force. And once we divide this force with the area, we'll calculate pressure. There are two important things that needs to be noted while solving these equations. First of all, they've already mentioned in this question that there are total of n number of molecules in this container, right? So first we are going to calculate the force due to one single molecule, and then we'll generalize this equation to calculate the force for total of n molecules in the container, right? To get the total pressure exerted by n molecules in the container. Then the second thing that needs to be noted is while calculating this momentum, we know that this momentum is the product of mass and velocity, right? And velocity being a vector quantity has its x, y, and z component. So in order to generalize this equation for one dimension, we are going to consider one single component of velocity. In our case, it is Vx, that is x component of velocity. We'll calculate the pressure due to this x component of velocity, that is pressure in one dimension, that is along x-axis. We are going to use the assumption that this Vx equals Vy equals Vz, which in turn leads us to state that this Px equals Py equals Pz. This is how we are going to calculate pressure in one dimension, be it along x-axis, y-axis, or z-axis. Let's get started. So first, we are to calculate the momentum. How do we calculate momentum? Momentum is the product of mass and velocity, right? They've told in this question that mass of one single molecule is m, right? No need to write m1, m2, m3 till mn because all the molecules in this container are identical. So we can easily drop the subscript. As for the velocity, since molecules here might not be moving with the same velocity, so we must differentiate their velocities. For suppose in order to represent the velocity for first molecule, we use v1, for second v2, for nth molecule we use vn. So here we are going to write v1, which represents the velocity of first molecule. But then, as mentioned earlier, for the sake of simplicity, we are going to consider the x component of velocity for the time being. So we must write this velocity as v1x, that is x component of the velocity of first molecule. This is the initial momentum, right? How do we calculate final momentum? Consider this molecule at this point somewhere moving along x-axis. Once it strikes this phase of the container, it is going to move back with the same velocity given that the collision is elastic. Just recall the postulates for the kinetic molecular theory of gases, in which we assumed that all these collisions are going to be elastic, and elastic collisions may momentum never changes, right? So we say that if the initial momentum was m v1x, then the final momentum should be m v1x with a negative sign, to show that after the collision with this phase of the container, the molecule is moving with the equal velocity but in the opposite direction. And then of course, collision does not make any difference to the mass of molecule, right? So the final momentum has to be this one. How do we calculate change in momentum? As mentioned earlier, change in momentum is final momentum minus initial momentum. Final momentum is minus m v1x, this minus from the formula right here, and the initial momentum is m v1x. Therefore, change in momentum comes out to be minus 2 m v1x. This is the change in momentum. We are to derive the expression for this time in order to calculate rate of change of momentum. Let it be A, B, C, D and E, F, G, H. Considering a molecule right here, right? We are to calculate this time interval, which is the time this molecule took to traverse this distance and then move back to collide with this wall of the container ABCD. In other words, we know that S equals Vt, so this T must equal distance over velocity. Distance or the length this molecule traverses to reach this wall back is L and then again L. So it has to be 2 times the length over velocity of the molecule is still v1x. Hence force, which is the rate of change of momentum, becomes F equals change of momentum minus 2m v1x over time it took to change this momentum. Let's just rearrange this equation. This 2 gets cancelled with this 2. This becomes minus m v1x square over this L right here. This is the force exerted by the wall of container on the molecules. Whereas we are to calculate the pressure, which depends on force exerted by the molecules on the walls of container. Using Newton's third law of motion, we already know that these two are action-reaction forces and they must be, therefore, equal in magnitude and opposite in direction. So if this is the force exerted by the wall of the container, then exact opposite, that is mv1 x square over L, should be the force exerted by the molecule on the wall of the container. Now that we know the force by one single molecule, we can generalize this expression for total of n number of molecules, and then we'll proceed to calculate the pressure. If the force due to first molecule depends on mass of first molecule, square of the x component of velocity of first molecule and the length of the container, then the force due to second molecule must depend on the mass of second molecule, which is m. We decided to drop subscript, remember. Then square of the x component of velocity of second molecule over length of the container. F3 becomes m v3x square over L, so on till this Fn becomes m Vn x square over L. How do we calculate total force? This total force must be the sum of all forces due to individual molecules. This becomes m v1x square over L plus m v2x square over L plus m v3x square over L till m vn x square over L. Let's just take the things common that we can. This mass right here is common between all these expressions. Let's just take it common here. And this L is also common between all these expressions. So this becomes m over L v1x square plus v2x square plus v3x square till vnx square, right? This has to be fx since we've only considered the x component of velocity, right? Now that we know fx, we can easily calculate px, which is force per unit area. Since they've mentioned that the container is cubical, length, breadth, and height are equal, that is capital L. We can write this area as L square since area of cube is the product of its length and breadth. This becomes px. Let's just put in fx here. This becomes m over L v1x square plus v2x square v3x square and vnx square. Whereas this L square has to be there, right? Now this px becomes m over, what do we write this L into L square? Of course, this becomes L cube, where this v1x square plus v2x square as it is. Do you see this mass right here and this volume in the denominator? Because cube of length for a cubical container is volume. Can we just replace this mass per unit volume with the density? Give it a thought. No, we cannot. Why? This m is the mass for one molecule, right? Where this L cube is the total volume available for total n molecules. This does not make sense. Either we take volume for one molecule and the mass for one molecule, or we take the entire volume available for n molecules and then the total mass for the n molecules, right? So what we can do here is density is mass per unit volume, total mass of the n molecules. If this small m is the mass of one molecule, multiplying it with capital N, which is the total number of molecules in the container, this right here is the total mass for total n number of molecules in the container. And now this L cube in the denominator is the volume available for n number of molecules. This is the right expression for density, right? Let's just rearrange this equation for m over L cube. Keeping this m over L cube here, this becomes density over n. So let's just replace this m over L cube in terms of density in this equation, because they sometimes ask you to derive the expression in terms of density. So this is how we introduce density in this equation. Let's just put in these values to this equation for px. This px equals m over L cube, which we are going to replace with density over total number of molecules times this whole factor, which is v1x square plus v2x square plus v3x square till vnx square. We can simply shift this n here, because we know that in case of multiplication and division, order does not matters, right? If we have 2 into 3 over 4, right? This becomes 2 into 3 is 6, 6 over 4, which is 3 by 2. Let's just change the order. 2 into 3 over 4. 3 over 4 is 0.75, and this 2 right here, this again becomes 1.5, and 1.5 is nothing but 3 by 2. Or you can also write it this way. 2 over 4 multiplied by 3. This 2 over 4 is nothing but half, that is 0.5, and then multiplied by this 3, this is nothing but 1.5. So it has been established that in case of multiplication and division, order does not matter. तो हमने बस उस n को यहाँ पर shift करवा दिया. We have 1, 2, 3 till total of n values being added and then divided by this total number n. This is what we call average. If we are adding 5 values and we are dividing it with 5, we say that these are the average values, right? So we are going to do the same thing here. We will write it as Px equals density, and then this becomes Vx square, and in order to mention average, we are going to place these pointed brackets here, right? This is the expression for Px. All we did was to replace this term with the average value. Since they are not V1x plus V2x plus V3x, there is a square here, right? So we need to take care of this square as well. This transforms into this equation. Abhi tak we have successfully derived an expression for pressure in one dimension, that is Px. But then this Px right here is in terms of Vx. We are yet to generalize this equation in terms of V only. So here we are going to considering the assumption that this Vx equals Vy equals Vz. So we can simply write resultant velocity equals under root square of x component of velocity plus the square of y component of velocity plus the square of z component of velocity. This, by the way, is the general equation to calculate the magnitude of resultant vector, right? Now putting these Vx, Vy and Vz equals Vx, we get V equals under root Vx square plus Vx square plus Vx square, right? And this becomes 1, 2, 3, 3 times Vx square. We get V equals under root 3 times Vx square, taking square to cancel this root. This becomes V square equals 3 Vx square. We are to find the value for this Vx square, right, in terms of V. So we can rearrange this equation as Vx square equals V square over this 3 here, right? Now just putting this equation in the expression for Px, we can write Px equals density, and then we have V square over 3 right here. And this 1 over 3 is just a number. Taking it out of this expression, this becomes density over 3 times the average value of velocity. This is the expression for pressure in one dimension, and the same is applicable for Py and Pz. We can write P equals rho over 3 average of V square, and the same applies for Pz as well. This is the expression in terms of density. So in order to transform this expression in terms of kinetic energy, we have to make a few basic changes, knowing that kinetic energy is half mv square. So we are to introduce mass in this equation and then a half in this equation. Let's just do this. Let me just change the color here to differentiate it. We know that pressure is density over 3 average of square, and we already know that kinetic energy is half mv square, right? So we can clearly see that this expression here lacks this mass and this half. How can we get half here? We can simply introduce a half here. We can multiply our equation with 2 and then divide it with 2 as well to balance this equation. So this becomes 2 rho over 3, whereas we can move this 2 in this expression and this becomes half v square, right? How do we introduce mass here? We don't need to multiply and divide with mass in this expression because this density already has mass in it, right? So we are just going to open this density in terms of mass, and this equation becomes P equals this 2 over 3 as it is, and we are going to replace this density with mn over v, and this value here as it is half v squared, average value of half v squared, right? Now all we have to do is move this mass here, because average value of mass and the mass of individual molecule are exactly same because the molecules were identical. So this becomes 2 over 3 n over v and half m v square. And since we know that this half mv square is nothing but the kinetic energy, this equation becomes this. And you can also replace this capital N over V with N naught. This is what you would see in textbooks. N naught, this one, where this N naught is the total number of molecules per unit volume of the container, and this P is the general expression for pressure, where this 2 and 3 are of course the numerical values. This N naught is total number of molecules per unit volume, where this represents average translational kinetic energy. Why do we say average translational kinetic energy? Because while deriving this expression, we just considered the translatory motion of the molecule. We ignored rotatory and vibratory motion of molecules. So therefore it has to be the average translational kinetic energy and not the average rotational or the average vibrational kinetic energy. You would sometimes see this equation without the constants here. How so? Since this 2 over 3 is constant, total number of molecules in the container are also constant throughout the process, and this volume of the container is also constant because we did not consider a container with a movable piston or something like that जिसमें volume change होना हमने allow किया होता है, right? So all in all, this n and this v is also constant. So we'll just simply replace this with a constant, and then there's average translational kinetic energy as it is, and we can always replace this equal and constant with proportionality. This becomes this. So we can say that pressure of the molecules of gas in a container is directly proportional to the average kinetic energy of gas molecules, and you'd see this written इस तरह से भी. How so? Because we know that average translational kinetic energy is the measure of temperature. We write average kinetic energy or we write temperature, एक ही बात है. This is the final expression in terms of temperature, in terms of kinetic energy, and then we have already seen in terms of density as well. This is where we end this derivation. See you in the next video. Till then, Allah Hafiz.